So if you turn to the notes that say AP level solution equilibrium problems, that is what we're working on today. These are all prime examples of how they put all this information together on the AP. I need you all to be quick with calcs. I need you to holler out what you want to do. I already know how to do this. I need to make sure you guys know how to do this. So we're going to start with this first problem. And the first problem says, a sample of 40 mils of a 0.1 molar acetic acid solution is titrated with 0.15 molar sodium hydroxide. The Ka for acetic acid is 1.8 E-5. Part A says, what volume of NaOH is used in the titration in order to reach an equivalence point? Anytime we do a titration, the first thing I want you guys to do is to outright show me a reaction of what's going on. Because if you don't have the reaction, you can't see what's going on and it's not going to work. So we're going to write whatever is going on in this step. And what are we adding to what? Acetic acid. And we're actually invading the acetic acid with the OH minus. The OH is what's in the burette, okay? And we're titrating a set amount of acid with this OH minus. And what do we make? Water and acetate. All right, so we've got that. Now the next thing to do is, since this is an invasion problem, this is basically a stoich table, what do we mean when it says reach the equivalence point? What's true at the equivalence point of a titration? OH and O acid have the same moles. So, do I know the moles of at least one of these? I must. Which one? Exactly. I know the acetic acid moles. So 0.1 times 0.04 is 0.004 moles. So if I'm going to be at the equivalence point, sodium hydroxide would also need to be 0.004 moles. Correct? Okay. So if that's going to be 0.004 moles, what do I need then? I know that, what do I know about the base? The molarity is equal to 0.150 molar. And what's molarity equal to? Moles over liters. See how I'd find those liters? Okay, so what is the liters? 0.0267 liters. On a burette, that would be about 26.7 mils. Is everybody with me? So that's question A. Question B says, what is the molar concentration of the acetate ion at the equivalence point? I'm just going to erase a little bit of this. Don't erase yours. You don't need to, because you can rewrite your stoich table if you have to. But what I want to do is, this is so not calibrated. I want to finish out this actual, y'all remember 26.7 mils, okay? Because we're going to need that. That's how much we needed. So I'm just going to write that 26.7 mils here. What is the molar concentration of the acetate? So at this point in the titration, how much of acetate do we have? None. We don't care. How much do we lose? 0.004. 0.004. And what do we gain? 0.004. So do you see how now we can find, so now the war is over, we have this left over. What is B asking for? Molar concentration. This is what unit on 0.004? Moles. So how do I find the molar concentration? What liters? The total. So we have 40 plus 26.7, so it's 0.0667 liters. So my concentration then of C2H3O2 minus is, give me more sig figs than that. I don't believe that for a heartbeat, that's exactly 0.06. 0.05997? All right. So this is my moles per liter. If I look up at my givens, I would report that to 3 sig figs. So 0.0600 moles per liter is what you could report. Not to 1 sig fig. We need 3 sig figs. All right. So now what we're going to do is answer part C. What is the pH at the equivalence point? So what was left over after the war? The acetate. So if this is all that's left over, what kind of problem is this? Hydrolysis. What do we do with that? Add it to water and put it where? In a rice table. So because I have to leave the problem available for people watching this on video. I think Grayson would like to do a shout out. Go ahead, Grayson. Dave and Nillen gets a shout out from Grayson, even though they're both sitting right here. Kind of feel like that defeats the purpose of the shout out, but and to his mom. He has the I Heart Mom tattoo. So now we're looking for the pH by this hydrolysis. So we take the ion, add it to water, and what do we make? Acetic acid and OH minus. Good. Okay, y'all are giving me hope in humanity again. I'm feeling a little bit better. Bless their hearts, 6th period, if you're out there listening. I told them to rewatch this, so they're listening to me now. This is what I sound like when I'm calm, 6th period. Very, very calm. Come on in, Miss Nelson. We're videotaping, but that's okay. Grayson did a shout out to his mom, so just say, "Hey, Nillen." Hey, Nillen. We're trying to give you sound bites, so. Get my note? Yes, thank you. I needed that. I needed that desperately after that department chair meeting. All right, so we need to find the actual pH. So we start out with our concentration. If you notice, you see how they kind of walked you through this? They went ahead and determined not only moles, they made you figure out the concentration. That's kind of a hint. They're going to make you use this for something, and that's what they did there. They're very nice at holding your hand and giving you some clues. Minus X, plus X, plus X. So we get 0.06 minus X, X, and X. So we get X squared equal to over 0.6, but we have a problem. And yeah, they give us a Ka. If you notice in your reaction, we got the Kb of that conjugate of the acetic acid. So we actually need the Kb. So I'm just going to go ahead and set it up so the graders know I did my conversion. 1.8 times 10 to the negative 5th. So we're looking for 3 sig figs, which is going to be an X. You don't have to round yet, because X, if we find it out, is equal to, I don't know why I put X in concentration brackets, because I'm trying to get this done fast and I'm making stupid mistakes. Oi. .77 times 10 to the negative 6 is equal to the X, which is equal to the H, oops, not H plus, OH minus concentration. If I take the negative log of that, I want POH to 3 decimal places, please. 5.239. Therefore, thank you, pH is good. All right, thank y'all for being speedy. It's going to help things. If you're watching this video and you get lost, stop, rewind, or just stop if you need time to catch up and write things down. That's the beauty about watching the video. You can stop and shut me up at any point and catch up. Are we good with this problem, though? All right, let's go on to the next one. This is a little dirty beast here, but we'll get it done. A says, it gives us a scenario. 1986, y'all. This is before I even took AP. It's a long time ago. It's pre-demo. Not pre-demo birth. I was in the prime of my youth at that point. I won't tell you how prime. In water, hydrozoic acid, HN3, is a weak acid that has an equilibrium constant, Ka, equal to 2.8 E negative 5 at 25 degrees Celsius. 0.3 liter, apparently they're British, of a 0.05 molar solution of the acid is prepared. Don't get confused between HN3 and NH3. This is not ammonia. This is an acid. That's an ionizable H right here. It's a weak acid, and it says write the expression for the equilibrium constant Ka. Well, I don't want that to scare you. Anytime you classify something as a weak acid problem, what were you supposed to do to that weak acid? Add it to water. If you do that, you're going to quickly recognize what your Ka expression is going to be, because you've written a ton of these. But this is the acid, so it's a proton donor, so what's my equation? Plus H3O plus, good. Okay, so now from that, I can write my expression. What is my expression? N3 minus times H3O plus over HN3 azide, all my concentrations. Part A is always a give me, and Part B is going to be a give me too. They're going to be something that you're really good at. In Part B, it says calculate the pH. What do? Rice table. So I've already got my equation here for Part B. Rice, baby. All right, what's my initial concentration of acid? Do I have it? 0.0. Do I care how much acid I have there? No. I only care about that if I'm invading it and I need to know how many moles I have, then I'd have to figure that out. But I'm just looking at concentration here. So we're going to shift right. 0.05 minus X, and X. Okay, so we set up, we have our Ka up there. My expression is X squared over 0.05. What does that equal to, Ka or Kb? Ka, so I got a Ka. It is 2.8 times 10 to the negative fifth. My X, which is equal to my H plus, let's go with, I don't care about the K, but that's going to dictate 2 sig figs. 0.001, 2 moles per liter. My pH then is 2.93. So we got that down. We got that down a couple units ago, right? All right. Now things start to get fun. Again, you don't erase. You have a whole page to do this on. I need to erase this. So I need to make room for Part C. Part C. It says that we are now going to take half of the solution we had earlier, and we're going to add 0.8 grams of sodium azide. The salt dissolves completely. Calculate the pH of the resulting solution. I never want you to freak out. I want you to jot down what you're adding to what. We're going to take 0.15 liters of what solution? 0.05 molar what? HN3. And we're adding to it 0.8 grams of the sodium azide. What do you think is important about that salt? N3 what? N3 minus. Huh. What are you doing there? Look at it. It's a buffer. Do you see how you just made a buffer? You took a weak acid and you added its conjugate. So how do we find the pH of a buffer? Henderson-Hasselbalch. To use Henderson-Hasselbalch, what do we need about the acid and its conjugate? What do we need of both of those things? Not moles. Concentration. We have concentration of this. We need concentration of this. For every 1 mole of this, there's 1 mole of that. So I need to find moles of sodium azide. Let's do that. 0.8 grams. For every 1 mole, thank you, there's 65.02 grams. So what's my moles? Let's go ahead and keep going. Once I know moles, moles are on top. I divide by liters. It all dissolves into 0.15. And the reason they say here, do they say assume no change in volume? Yeah. They say if the volume of the solution remains unchanged, that's what's allowing you to divide by that 0.15. 0.082. Does someone else get that? All right. 0.082 watts. Moles per liter. And the reason I can do this, again, I had to use the full molar mass of sodium azide, right? But for every 1 mole of that, I had 1 mole of that. I am dying. Teacher's aid. Give me some water, please. I like how Peter's totally clueless. Sorry, people out there. I really can't breathe. Someone else needs to take over because I can't breathe. All right. Fantastic. So now that we have the molarity of the conjugate, what do I do to find the pH? Thank you. Use Henderson-Hasselbalch. Correct. pH or POH version? pH. That's going to be the worst sounding video on the planet. He didn't give me DI. You didn't give me DI water, did you? Did you give me tap water? Okay, good. No, I'm not worried about the fact it's DI. I'm worried about the fact it sits there for months. That was funny. Okay, I'm going to tell a story, and I'm on video here. So we had a sub who will remain unnamed. This is a lady I've never used again. She apparently was very mean to everyone, and everybody hated her in the class. And she wanted something to drink, and so someone said, "Oh, there's igloos in the back." So she goes back there and fills it. There's ants and stuff in the igloos. She fills up her thing and drinks it, and the kids just sat there silent, not suggesting, "Not a good idea, ma'am." They let her drink. But who would do that? Who would go to a chemistry lab and just fill up their cups without knowing? I don't know. I wouldn't do that. Apparently a substitute teacher. 2.8 times 10 to the negative fifth? Okay, plus the log. What do I put on top? The ion, which is the 0.082 concentration, over the concentration of the original thingy, the acid, which is 0.05. So what is our pH? Louder? Thank you. 4 point. Everyone else get that? All right. That's not too shabby. We made a buffer. What throws people off, though, is all this other little junk that you have to do. They don't give you moles. They don't give you molarity. You got to figure out the molar mass, and then you got to find the. It's just a lot of steps. Just always keep your vision of what you're getting to in your head, and you're going to be fine. So this next one, we're going to take the other half of that solution, and we are going to do what to it? I heard it louder. Invade it. We're going to invade that solution with some sodium hydroxide. So we have that HN3. Invasion equation, I always want you to write first. What does that make? Water and N3 minus. So since this is now an invasion, what do I put in this table? Moles. I have 0.15 liters of the original solution, which was at 0.05 molar. In this one, I do care about how much we used. How many moles is this? 0.0075? All right, and then the sodium hydroxide, I have 0.1 molar of 0.075. Oh, looky there. What does that tell us? We're going to lose. If this were a titration, what would we be at? The equivalence point, but we don't know if it's a titration. Probably isn't. All right, so that's going to give us 0.0075 moles of this. What kind of problem do we have left over now? Yes. High five. A hydrolysis problem. So in order for us to do that, we have to take what? We have to convert moles to what? Molarity. We're going to divide by total. This is where you got to be careful. We had 0.150 liters of this thing and 0.075 liters of that. Math is so hard. 0.225 liters. So what's my molarity to 3 sig figs, or actually 2 sig figs? Point what? 0.033 moles per liter. All right, what do I do with that 0.033 moles per liter? Rice table. How do I start my rice table out? N3 minus plus water. I'm in equilibrium now, so I have an equilibrium sign. HN3 plus OH minus. So our original concentration of this is 0.033, 0 and 0. Got to shift to the right. 0.033 minus X. I can trump. Notice I'm not caring. These problems get so convoluted they're not going to expect you to worry about including or excluding X. When I set this up, what do I need though? A KB. Again, every time we do a hydrolysis problem, we got to do that flip. X squared over 0.033 is equal to 1 times 10 to the negative 14th divided by 2.5 times 10 to the negative 8th, which is the KB of the HN3. X, which is equal to the OH minus. Please continue to write this to get your AP point. What? I didn't hear the first one. Okay. POH. I can't hear you all the first word. 5. And then we only, oh, thank you. We only needed the OH concentration. My bad. So this is in moles per liter. Bad teacher for not reading the instructions. Good job. Feeling good still? You ready to be destroyed now? I'm just kidding. We'll see. I'm going to have to lead you through some stuff, but you're going to have to pull out some things from ghosts past, from times past. All right. First couple are easy. From the systems above, identify the conjugate pair that's best for preparing a buffer with a pH of 7.2. Now, when we say best for preparing a buffer, we probably want to go ahead and make an effective buffer. So tell me, thinking of Henderson-Hasselbalch, what does it mean to be an effective buffer? Sexy statement. What? The same concentration? So what does that do to Henderson-Hasselbalch? He said the same concentration of acid and conjugate. Correct. Exactly. So our Henderson-Hasselbalch is just this. Right there, you've answered your question. What do you have to do now to figure out which of the ones above will give us this pH? Yeah, if we take the P of the Kas, negative log of these Kas, we can figure out which one's best. So go ahead and read those to me just so people at home will have these values. Okay. And the last one I know this is the right one. Now let me ask you this. Looking at those Ks, can y'all kind of guess which one was closest to 7.2 without doing the calculator? Kind of. I mean, if you look, you see how that's going to get you closest? You kind of need to start looking at logs and know what's going on. Yes, ma'am? Sure. Okay. Shravya had another option of going the other way. Same difference. You could have said, okay, I'm going to go 10 to the negative 7.2 and find which of the Kas is closest. That works too. Either one of those would have brought you to the acceptable answer. As far as how to explain it, I would say what I did. I'd say that the most important thing is to state that, and I'm not going to write all of this down. You guys can be writing this down, and at home you can stop the video and write it down. It's important for you to say that in an effective buffer, pH equals pKa, and that's what we're looking for. So to have a pH of 7.2, we would need a Ka of whatever. Or you can say the first one would have a pKa of this, the second one would have a pKa of that, the third would have a pKa of that. I'm choosing this one closest. Something like that. But show your work somehow of what you did to figure that out. Just saying buffer number 2 isn't going to cut it because of the fact it says explain your choice. Now, some of you have a hard time not explaining things. If this problem just said which is the best, don't explain it. Okay, there's been a lot of fights in the grading where people have said, but they didn't say why, and we're like, it doesn't say. If it doesn't say explain, don't explain. Just say the second one, and you'll get credit. Okay, it's very literal on how it's graded because they can't be mad at you if they didn't tell you to explain it. Does that make sense? Because if you explain it in a weird way or don't say something right, you could potentially lose your point. All right, but here they did say explain, so that's not an issue. Part B, explain briefly how you would prepare a buffer as described with the conjugate pair you have chosen. So in Part B, that conjugate pair we chose was H2PO4- and HPO4- minus 2. You've kind of already answered this question by saying pH equals pKa. So what does that mean? What would you do when you made it? You're kind of reiterating something. You'd mix what? You could say equal moles in a certain volume, or you can say mix equal concentrations of the same volume of each solution. Or you can say you would mix equal moles in a set volume, something like that. You just want to indicate whatever you're doing, you're putting in the same. And when you do that, I would go so far, y'all, just to cover my bases. And I would put, so it's the ion, the one with the more stuff. That's the acid. I don't care which one you put on top. It would still work. So proton donor, you put this one on the bottom, H2PO4. They won't, as long as you show that you know those cancel, I would just do that. And then by doing that, you would prove your point and say that the negative log of that 6.2 times 10 to the negative 8th is equal to the 7.2. Okay? All of that stuff is saying the same thing. Is everybody good so far? All right, part C. The concentrations of both the acid and the conjugate base you have chosen were doubled. How would the pH be affected? And I'm not writing this down, folks. You can write this down. How would it be effective if we doubled the concentration? What would happen to the pH? Come on. Yeah. Why would it be the same? The ratio stays the same. So you can say the pH would be the same because the conjugate acid to base ratio remains the same. But how would this affect the, what do they say, the effectiveness? The capacity is what they say. How would this affect the buffering capacity? Yeah, I'm a little wary to say it's doubling the capacity, but yeah, you could say the capacity increases. I can't think of any reason not to say doubling the capacity. I just get nervous about that for some reason. Probably in the middle of the night I'll wake up and say why you shouldn't say that. Can't think of it right now. I'm okay with it. But you know it increases, so that's the safe. It didn't say how would it didn't say explain how the capacity of the buffer is affected. They didn't say, if they wanted you to say double, triple, quadrupled, or whatever, they would have given you better direction. So just say it increases the capacity and you're safe. So meaning it can take more hits from the acid and the base side because there's more moles in every liter. All right, this is the tough part. This goes back to that lab we did. Explain briefly how you would prepare a buffer if you had available the salt of only one member of the conjugate pair. So say we had sodium NaH2PO4 or Na2PO4 and a strong acid and a strong base. How did we do this? This is not hard. Here are my two components. I don't care which one we choose, but what we can do is we can invade one of those with either an acid or a base and make the other. That's how you make the buffer. So what you remember what you did in that lab, you had your beaker and it had your weak acid in it. And you took half of that, right? And you added what to it? Don't say phenolphthalein. What did you add to it? OH minus. What you did was you converted this with an invasion to that. You converted that in the amount of half. So you took half of this, converted half of it to the same amount of that. Make sense? And you mixed it back together. What did that mixing back together do to HA and A minus's concentration? It made them equal, exactly. So HA and A minus were equal, and at that point, pH is equal to pKa, right? So the question that you want to ask yourself is, okay, pick either one of those, and then you have to know whether it's an acid or base you need to add, which is not hard. Which one do you want to choose? I don't care. -2. Okay, we're going to choose this one. What do I have to add to this weak acid or base to make the conjugate? No, weak acid or base, and you say water. What do I have to add to this to make this. OH minus. No. That's not an option, guys. Look up here. If you had available salt of only one member of the conjugate pair and a strong acid or a strong base, what are we going to add? H plus or H3O plus. What does that make then? It makes H2PO4 minus. Everyone see that? If I would have chosen this one, what would I have had to add? No, water is not an option, Nilin. Oh my God. I'd add the other, and then I would lose an H and make, oh my God, HPO4 minus 2. Do you see that? All right. So what you have to do in this problem is say which one. So we'll just say we take H2PO4 minus salt solution. By that, they're just saying it doesn't come like that. It has to have a sodium in front of it to be a salt. You would add strong acid. Now, we got to get a little more detailed. We would add enough H plus to which one again? HPO4 minus 2 to do what to it? How much of it? To neutralize. Aren't we neutralizing? Yep. To neutralize half of it. At which point, what's true at that point? Sexy. pH equals pKa. And there you have it. Y'all did better than expected. It's okay. But now, again, I'm ready to beat you for the next one because this is going to take you back to the first titration we did. Any questions on this one? All right, last problem. Oh, what is this? It's a titration curve, right? Tell me some things about this curve without even reading. What are some things that you can see? Is the middle of the sharp rise? It's about here. Okay, so what can you tell me that this is? Weak acid because this is pretty high, and strong base. Okay, good. A 30 ml sample of a weak monoprotic, what does that mean? 1H. All that means is that 1H plus is coming off. If we had a polyprotic, the curve would look like this. You'd have an equivalence point for every single H, but they're just saying that this is the only equivalence point. Was titrated with a standardized solution. This is the part you don't know, and I'm going to tell you right now. When we say standardized, it means somebody went and did a separate titration to verify the molarity of that thing. So what this is telling us is that the molarity is known. That's an important point. We're going to do this problem without using necessarily numbers and crunching numbers, but we can say how to solve for things if we know that molarity. Okay? We have 30 mils in a beaker, titrating it with a known concentration of sodium hydroxide, and we made that curve. A pH meter was used and made this curve, and we have to answer some questions. A, how would this curve be used to determine the molarity of the acid? Go back to before you knew anything, and you made this curve on the LabQuest, and you were supposed to find the concentration of this unknown acid. You went somewhere on that curve straight up without knowing anything. Where did you go? Yeah, that's kind of a high five, but that's not what we need to do because that's a lot of, I'll explain that in a minute. If we get done before the bell rings, Grayson had a really good point, but there's a problem with that, and I'll tell you why in a minute. Where do we go? The middle of the sharp rise. Remember going there? That's called the what? Equivalence point. What's true about the equivalence point? Moles of acid equals moles of base. All right, we need to get to concentration of acid because that's what we're looking for. So we probably would be good if we knew moles of base maybe. Do we know moles of base? We know the molarity We know that. It tells us we know that. What else do we know? Yes, the amount. Very good. We're going to say that's about 24 mils. It's as good as we're going to get. So how do we find the moles of base then? We take the molarity of base times 0.24, and that's going to give us moles of base. Is everyone with me? So now what do I know? If I know moles of base, what do I know? Good. How do I get to concentration of acid? Not 30. Total. Oh, no, not total. My bad. It's not total because we're looking for, my bad. If we put in 26 mils, that's not what we're looking for. We're not looking for the concentration of the acid after the mixture. We're looking for the concentration of H pluses originally. And we originally have the 30 mils in there. Yes, for once you were right, Elliot. High five. All right, so we're going to divide by what? 0.03. And that's going to give us the molarity of acid. I'm not literally crunching numbers here, but I'm showing how I would do it. Are we good? Part B, different problem. Explain how we use this curve to determine the Ka. What do you think? We talked about this on Friday. How can we use this curve to find the halfway point, midpoint? Very nice. So if we know that the equivalence point is about 24, where would the midpoint be? About 12. So we're looking about here. What will we do? What's true at the midpoint? Nice. pH equals pKa at the midpoint. Oh, you guys give me hope for a better tomorrow. All right. So if we know that the pH then is about, let's just say 5, you don't need your calculator. If the pH is 5, what's the Ka? 10 to the negative 5th. Bam. Good. Now, we're going to cover indicators in much greater detail in the next couple of days. But what you need to know about an indicator is an acid or base that will change color at its something called the endpoint. Okay? When it changed color is at its pKa. pKa when indicators change color. Now, we're doing a titration. We don't have a pH meter. We want the indicator to change color near the equivalence point. So what pH-ish would we want the indicator to change color at? 8-ish, right? So if we want the indicator to change color at 8, we need an indicator that has a pKa of about 8. Which indicator has a pKa of about 8? Cresol red. Now, people earlier were thinking we were in the midpoint. We were looking for the change here. No, no. That was just to find the K of the acid. Okay, when we're looking using a color, thing that changes color, like phenolphthalein or whatever, those are acids that have their own pKas. And an indicator changes color at its pKa, and that's known as the endpoint. The endpoint is when an indicator changes color. So the most effective titration with an indicator will be when the endpoint and the equivalence point coincide. Phenolphthalein is a little interesting, and we're going to talk about that because you're going to get a new appreciation for phenolphthalein in a few days, if you don't already appreciate how awesome phenolphthalein is. Okay, last part of the problem. You guys will be fine on this one. This is what you'll rock at, I hope, because this is the final bit we did on Friday. The question is asking us to please sketch the titration curve that would result if the weak monoprotic acid were replaced with a strong monoprotic acid such as HCl. What would be different? We're going to draw it right on top of this. It starts lower, okay? What's another important thing? pH at 7 is the clue here. I want this right here to be the middle of my rise. It's going to be sharp, so I want the rise to be about double in length, right? And then, phew, it's going to start lower. It's going to be flat. It's going to have a sharper rise, and then it's going to end. Why is it going to end exactly the same? Wasn't it a stronger acid? It's the same base. And remember, we're invading our base into the acid. There's going to come a point, strong or weak, all the H is going to be gone. And that's the only thing that's going to be creating pH. That occurs past the equivalence point. Once you hit the equivalence point of the acid, the exact same situation happens since the base is the same. Good? That was tough. Good job, y'all. Give yourselves a hand.